Welcome to Calculus for the Average Student. I'm Ben. Today we're going to be talking about the fundamental theorem of calculus, but before we get started, let's do a little review. So, what if I gave you a graph that looked like a rectangle per se, and asked you to find the area under that rectangle? How would you do that? Glad you asked. So what you would do is you would simply take the width of the base times the height, right? Because that is area. So what if I made things a little more difficult and said, all right, now your graph's curved, and you have to find the area under that curved graph. And I'm not talking like a circle that you could just use pi r squared or something like that. It's irregular and it's curved. So what would you do? Well, this is where calculus comes in. There's a little trick that we call a Riemann sum. And basically what it does is it takes a section of that curve and divides it into smaller sections. Each section is then turned into a rectangle. And basically what we do is we take the width of that section times the height of the rectangle and multiply those together and we get the area. And then we do that for each of those rectangles in that section of the graph and successfully find the area under the curve. Now, technically this is only an estimate because we can never get a horizontal line to match a curve. It just doesn't work. Now, the way to get more precise is to make those rectangles smaller. So if we took each rectangle and made it infinitely small and put an infinite number of rectangles within that section of the graph, we would get a much closer answer to the actual area of the graph. And this is what we call integration. Now, basically, integration, there's a formula, and it's the integral from a to b of f of x dx. And it looks really complicated, but we're going to break it down so it makes a little more sense. So basically, we're going to address the inside first, and then I'll talk about that s-looking thing. So the inside, the f of x part is really just a function. F of x is the same as y equals some function, let's say x squared plus 4. Now, f of x, for our purposes, is going to be the same as the height. Whatever x value you plug in for x in f of x will give you a height value, and that's the height of the rectangle. Now that little dx part, technically that means an infinitely small change in x. For our purposes, it's going to be the width. Now the width is going to be infinitely small, and if you think about what I was saying earlier, it makes sense that our width would be infinite because we have an infinite number of rectangles within that section of our graph. So basically, once we've multiplied the height, f of x, times the width, dx, we get the area of a rectangle. Now, this is where that s thing comes in because we don't want the height of just one rectangle. The s thing is saying the letter on the bottom, the a, and the letter on top, the b, those are the limits. So we go from a on our graph to b on our graph, and that marks the section of the graph that we're taking the area of. So basically what the s thing is saying, is take all those little rectangles that we made with infinitely small changes in x from a to b, find the area of each rectangle and add it all together to find the total area. Now technically this is still an estimate because we still are using horizontal lines and there's still a curve, they're not going to match. But the deal is we can call it exact because we are so close, the rectangles are so small that the margin of error becomes indefinitely small and in sense can be considered negligible because of how minute it really is. So the equation that I've given you, we're going to expand on that in a second, but first we want to go over a few derivative things to make sure it makes sense. So have you ever wondered what the dy over dx means? Now, from what you've been told, it's just notation for taking the derivative, but really it makes sense if you expand on it a little. So what I was saying earlier about the dx being an infinitely small change in x, well, dy is actually the same, except it's in respect to y. So it's an infinitely small change in y. So an infinitely small change in y over an infinitely small change in x is the same thing as a change in y over a change in x. And if you remember back to algebra and pre-cal, y2 minus y1 over x2 minus x1 is slope. So dy over dx is the same thing as slope. So what you're really doing when you take the derivative of an equation is you're finding its slope. Now, it'll give you an equation, you plug in an x value to actually find that slope, but essentially that's what it's doing. So with that in mind, the notation when you've taken the derivative of f of x, you just do the little prime thing, right? Little prime f of x, so f prime of x. Now, for integration, there's a similar notation. when you take the integral, the indefinite integral of a certain equation, the notation for that is a capital letter. So if we were doing f of x and we took the integral of f of x, it would be capital F of x. And all that means is that it's the integral of the original equation, which we call the antiderivative. So, taking that into consideration, the theorem I was going to tell you about a sec ago, we're going to go ahead and do now. So, basically, it's saying that the original integral equation that I gave you, the integral from a to b of f of x dx, is equal to f of b, capital F of b, so the antiderivative at b, minus the antiderivative at a, so capital F of a. Basically, the way you would use this is, say I gave you a velocity graph and said, well, we need the area from a to b. So find the area from a to b, and then once you've done that, I'll give you the position, let's say, at a. Now I need you to find the position at b. And if you remember to integration of position and velocity and such, if I give you velocity and you were to integrate it, it would give you a position graph. So what I'm doing is I'm giving you the antiderivative of the velocity at a certain point. Now, the other endpoint, which is b, you can find the position at that point if I gave you the position at a. So basically what you do is you find the area, you set it equal to that point that you're trying to find, the position you're trying to find, minus the one I gave you, which would be the point at a. And you can do the opposite. If I gave you b, you could find a, as long as you have that area. So, so basically, that's part one of fundamental theorem of calculus. There's a part two. Part two is very simple, and it hasn't seemed to have a lot of applications so far. But basically, what you do with it is, it's taking the derivative of an integral. But the special situation in this case is that the second limit, so not a but b, is a function, or in this case x. So what basically all that you do is once you've taken the derivative, you cancel the derivative and the integral parts cancel out, and all you're left with is replacing the letter in f. So in this case we'll do f of t. So you're replacing that t with the upper limit, which is x, and that's really all it is. So instead of doing some crazy integral and then taking the derivative of it, all you do is swap the inner function with that upper limit. So how would all this stuff apply? Well, we're going to talk about one application today, and we're going to talk about cars. So when you're driving along, have you ever wondered why can't your car just keep going at one speed the whole time? Well, there's a lot of variables and a lot of reasons, but basically this really explains one of the needs for calculus. If your car was able to keep one constant speed for an amount of time, then the velocity of that car would just be a horizontal line, and we could find the area very easily. But since that's not the case, we need calculus. Now, if we have, say, the velocity of this car, and it's going along, it's kind of curvy, something like this, and let's say there's a wreck in front of it and it has to stop. It's not just going to immediately drop off and hit zero. If it were, everyone inside the car would die, and the wreck would probably happen anyway. But basically, the car has to gradually slow down. It's just not physically possible for the car to instantaneously stop. Now, there are times when the speed is decelerated a lot quicker. For example, if the car were to hit a wall, it would decelerate a lot faster than if you were braking. But it still can't go from 60 to 0 instantaneously, just like a car can't go from 0 to 60 instantaneously. So basically, all of these problems give us a lot of curved graphs, and so basically requires the need for calculus to integrate those graphs and to derive those graphs. You have to have the calculus. So basically, if you go from position, if you have the position graph and you want to find velocity, all you have to do is take the derivative. If you take the derivative of position, you get velocity. If you take the derivative of velocity, you get acceleration. And there's actually one more application that's practical. If you take the derivative of acceleration, you actually get what's called jerk. Jerk is really just a change in acceleration, just like velocity is a change in position over time. So, and if you think about our derivative equation, d over dx, dx is your change in x. Now, if your change in x is change in time, like in this case, our y value on position graph would be the position, and the x value would be our time. So it's giving you the position at a given time. So when you take the derivative of position, you're dividing the position by the time, which gives you, so say our position was in feet and our time was in seconds. If you take the position and derive it, you would get feet per second, which is speed, right? If you did that again, you would get feet per second squared, which is acceleration, and etc. for jerk and so on. But there's no real applications after jerk. So basically, all this to say, if you have the position, or say you have the acceleration, you can do the same thing backwards to get from acceleration to position. You just integrate it. So you take the integral of acceleration, you get velocity. You take the integral of velocity, you get position, and so on. But the only problem with integration is you have to have an initial condition, because when you take the indefinite integral, you end up with that c variable, and you have to solve for c to actually get a true equation. So that's the only catch to it, really. But if we have any of these situations or graphs, then we could use the fundamental theorem of calculus to find, so say we have velocity, right? We could take the area of the velocity curve, and given an initial position, we could find another position on that graph in this case, of the car. So yeah, those are the applications for the fundamental theorem of calculus, and thanks for joining us.